Topic is potential energy. Potential energy is the energy of an object due to its position or state. Yes, two terms are used. Either due to its position, it has some energy. That means the object has some energy. Or due to its state. Okay. When an object has potential energy, that means it has the potential to impart motion to another object. Okay. It has the potential to impart motion to another object. Means it has the potential to do some work. Okay. Here it means the object. I am talking about the object. Okay. So, two types of potential energies are there. One is called gravitational potential energy. Another one is called elastic potential energy. I think you are familiar with gravitational potential energy. When an object is raised above the surface of earth, the object gains some energy which is called potential energy, and which is equal to mgh, where m is the mass of the object, small g is the acceleration due to gravity, and h is the height which is measured from the surface of the earth. But it is always not necessary that always you should measure the height from the surface of the earth. Actually, in the calculations of physics, change in potential energy is required for most of the calculations. So, instead of taking the surface of the earth as the reference line, you can choose any line as a reference line to calculate the potential energy, but that reference line must be a horizontal one. Means that reference line should be parallel to the surface of the earth. Yes, we are talking about everything with respect to earth. For other planets also, you can simply apply the same principle. Okay, so potential energy is how much? You know this formula mgh. How this was calculated, how this was derived, the formula mgh, because it was derived using the formula for work. You know that work done, it is equal to force multiplied by displacement. Means work done is defined as the product of force and displacement. Say there is a little displacement dx, means infinitesimally small displacement dx, and F is the force, then what is the work done? F dx. If you are moving the object of mass m away from the surface, away from the center of earth, okay, then in that case work is done on that object, because you are taking away the object from the attractive force of the earth. So you need to do some work on that object, and that work done on that object will be stored as potential energy. So what will be the work done in that case? That will be equal to integration of f dx. Dx is infinitesimally small quantity. This is used for displacement. Then f dx is the work done for the small displacement dx. So for the total displacement, say displacement is from 0 to L. Okay, initial position was 0, final position was L or H. Better to say H. Okay, 0 to H. Then it is integration of f dx. I can write here integration of f dx, and x varies from 0 to L. Okay, this is the work done denoted by W. Okay, 0 to L. F is the force. F is how much? F is equal to mg, where m is the mass of the object, g is the acceleration due to gravity. I don't know whether this red color is visible or not. If not visible, then I'll write everything on the screen. Okay. So F is equal to weight of the object, which is equal to mg. Now you put this mg here and then perform the integration, you will get the result is equal to mgh. You will get mgh. So here g has been, this small g, which is acceleration due to gravity, has been taken to be a constant quantity, and this g can be considered as a constant when the height h is small as compared to the radius of the earth. Okay, but if the height h is not small as compared to the radius of the earth, in that case you have to take into account the variation of g also. Means in that case g will not be a constant, g will be a variable, and taking into consideration that thing also, you need to perform the integration, and the result will be different. In that case the result will not be mgh. Okay. Anyway, you know how this can be considered. Okay. The effect of change of g due to the change in height. That formula is known to you. Put that formula and then perform the integration. You will get the result. Anyway, so this was all about the potential energy, but it is gravitational potential energy. Next is elastic potential energy. You know, springs can become compressed, spring can be expanded. Means from its equilibrium position. Say a helical spring is there and no force is being applied on that spring. So in that case the spring is in equilibrium condition. Now you can either expand the spring or you can compress the spring. In both the cases the spring will store some energy, and that energy, when you are removing the force, you are withdrawing the force, applied force. Okay, applied force means what? The force by which you expanded the spring or you compressed the spring. I am talking about that force. When you are removing that force, when you are withdrawing that force, then in that case the spring will be able to do some work. So energy which is stored in the spring due to expansion or compression. So this expansion and compression, a single word can be used for both the cases, that is called deformation. So due to the deformation of the spring, some energy will be stored in the spring, and that energy is also called potential energy. So this is what kind of potential energy? This is elastic potential energy. This is also called strain energy. S-T-R-A-I-N, strain. This is also called strain energy. If you are a student of engineering or a student of physics, I think you know this term, strain energy. Okay, and you know the formula, half k x square, that formula is used for the calculation of potential energy, elastic potential energy, where k is the stiffness, which is measured, which is equal to force per unit deformation. Say for the deformation of delta, force required is F. For the deformation of delta, small delta, okay, required force is F. Then stiffness of the spring K, okay, K is equal to F divided by delta. Here K is the stiffness. So unit of stiffness will be what? It will be force per unit length, that is SI unit will be Newton per meter. Newton per meter will be the SI unit of stiffness, and in this case also work done will be calculated, or the formula for work done will be derived in the same way. Basic formula is this one, integration of f dx. Here also you apply integration of f dx to calculate the work done. Okay, here f is not a constant. Here f was taken to be a constant, which was equal to mg, but here f is not a constant. F is equal to how much? Using this formula we can say that f is equal to k into delta. Right. So if you put integration of k delta and here dx, okay, here x varies from 0 to delta. Here x varies from 0 to delta, and this delta is nothing but x. Instead of writing dx, you write d delta, or instead of writing this delta, you write x. So it is integration of kx dx. So what will be the result? Half k delta square. or if you do not change delta, you just keep it as x, then the formula will be half kx square. Okay? Here, x and delta both are same, they are not different. When you are expressing the length by delta, then instead of writing dx, you should write d delta. And if you are interested in writing dx, then the deformation of the spring should be taken as x. Okay? Then in that case, that is equal to, means in the calculation of stiffness, then that is equal to f by x, that is k. F by x is equal to k. K is stiffness. Anyway, actually this was very easy topic. I think I should not take any more time to explain both the cases. Okay, both the terms, elastic potential energy and gravitational potential energy, both are very easy. Both the terms you will find in the chapter of mechanics. Okay. Anyway, so this is the end of this video. Thank you. Thank you for watching this video.